Our topic today is the famous four-color theorem. It states that no more than four colors are required to color the regions of any planar graph so that no two adjacent regions have the same color. Our goal is to examine the math behind the four-color theorem, a problem which can only be solved by a computer while being a common application in our everyday life. We're also interested in the basis of the graph theory associated with the four-color theorem as we learn about path, edges, and vertices of a graph in our class. It was first conjectured in 1852 and proved in 1976 by Wolfgang Haken and Kenneth Appel. There was a famous attempt to prove using strong induction by Kemp in 1879. He tried to prove that a maximal planar graph must have at least one node with degree 5 or less. So he used Euler's theorem for planar graphs and a counting argument to show if all the nodes had degree 6 or higher, then the graph would not be planar. So if the maximal planar can be four-colored, then so can graphs with fewer edges. But there was a flaw found 11 years later, which were abnormal, but removing the flaw, a five-color theorem still applies. So later on, mathematicians who were interested in this problem tried to solve a four-color theorem with aids of using computers.
So now we're gonna go through the process of the four-color theorem being proved. So proving the four-color theorem was a very difficult process, at least for the mathematics world. So time and time again, it went through a roller coaster process of being proven and disproven again. So the theorem went again and again from being a conjecture to a theorem. So originally, as we all know, the four-color theorem was used for maps and like geography. But so to prove this, mathematicians try to turn this map into a planar graph. So what they would do is they would assign each region with a vertex to turn this map into a planar graph. So for example, here we have the region D that will be turned into the blue color region D will be turned into a blue color vertex D. Same goes with A, B, C for the four colors. Um, so this was way back in like 1700s or 1800s where um people had to manually prove on paper of for the math theorems. So in 1879, Alfred Kempe published his unavoidable set, which for centuries was believed to be believed to have proven the four-color theorem. So on the right, we can see this is a picture of his unavoidable set. So in this unavoidable set, he proved that we only need four colors for maps or um, assigning assigning colors to uh, regions on a map. So for for a few centuries, Alfred Kempe's unavoidable set was believed to finally have proven the four-color theorem. But unfortunately, it was disproved later on by other mathematicians. So for a while, the four-color theorem was back to being a conjecture for a pretty significant amount of time until 1960. So in 1960, Wolfgang Haken and Kenneth Appel, they utilized the power of supercomputers. So in the 1900s, the supercomputers were finally invented. So they could finally use the powerful computing power to really act as a catalyst for proving or like calculating math theorems and math work. So these supercomputers have the ability to find many different possibilities that would take a long time for humans to manually do it. And it's a computer, so it doesn't have much error. So I guess it's more trustworthy. So in the end, they found a set of 1,936 reducible configurations, which essentially means that a minimal counterexample cannot occur for it to be disproved. So uh, this reducible configuration says that there cannot be a counterexample to disprove. So nothing can be said for sure in the future, but with the technology we have now, uh, it is sure that this latest theorem in 1960 for the four-color theorem has been proven and it cannot be disproved. So here's a picture of the powerful supercomputers in the 1960s, and this is a snippet of the reducible configurations that Wolfgang and Kenneth had to prove the four-color theorem.
So, moving on to the extended topic of four-color theorem. First, we have the three-color theorem, which has the goal to color the graph using only three colors so that no two adjacent vertices are colored with the same color. And it turns out that we can use Grobner basis to answer the question of whether or not a particular graph G is colorable. Some applications of this theorem is to apply in certain planar graphs, like some type of triangulation or special case of bipartite graphs. And compared to four-color theorem, three-color theorem is applicable to a more restricted set of graphs. Next, we have five-color theorem, which is a result from graph theory that given a plane separated into regions, such as political map of the countries of the world, the regions may be colored using no more than five colors in such a way that no two adjacent regions receive the same color. The five-color theorem was actually based on a failed attempt at the four-color proof by Alfred Kempe in 1879, where Percy John Hewood found an error in 11 years later and proved that five-color theorem based on Kempe's work. The application for five-color theorem is actually pretty similar to four-color theorem, which is it can be used in cartography to color maps where in region correspond to vertex and edges represent shared borders. While compared to four-color theorem, five-color theorem has a simpler and purely mathematical proof without the need of computer assistance.
Application of four-color theorem in real life. Unfortunately, there's no major real-world application beyond the obvious that one only needs four colors to color map. Famous theorems in mathematics are not always famous due to their applicability. Like Fermat's last theorem, the four-color theorem is famous for being simple to state and incredibly hard to prove. Similarly, Gold-Batch conjecture, the Collatz conjecture, and the twin primes conjecture are all very easy to state, but have almost no real-world application. Sometimes we study theorems because they are beautiful or interesting. Sometimes we study theorems because they're useful. And the four-color theorem belongs in the first camp. However, there is still some real-life application for four-color theorem. A cartography application of software can utilize the four-color theorem to automatically generate color schemes for maps. And the other one I can think of is the mobile phone mast. These masts all cover certain areas with some overlap, meaning that they can't all transmit on the same frequency. A simple method of ensuring that no two masts that overlap have the same frequency is to give them all a different frequency. And four-color theorems do apply in this scenario. Conclusion. So in conclusion, we went over the four-color theorem and the proof, as well as some extension of the four-color theorem, which is like three-color theorem and five-color theorems. I hope you guys enjoy our presentation. Please let us know if there's any more questions. And this is our resources page. Thank you for listening.